Welcome back. In this section, we'll be talking about mathematical models, creating equations that describe certain scenarios. So this is sometimes for people the trickier sort of thing to do. It's not as easy as a nice little procedure like completing the square where I can lay out the rules on how to do something like that. This is something that takes a little bit more creativity on your part. And this is something where you'll need to create an equation, some sort of function that describes something. And this will often involve maybe something geometrical, so things like areas of squares or areas of triangles. Maybe it'll involve things like distance formulas or midpoint formulas. And so some of the things that you might want to do would be, I suggest maybe making a drawing. So if it's something that has a geometrical interpretation, a drawing would make sense. If what is being described is something that takes place on the X and Y plane, maybe draw that. Thinking about if you have variables that need to be defined, what do they represent? In cases where X and Y are representing X coordinates and Y coordinates, that's pretty obvious. But maybe you're thinking about things where it's not on the X and Y plane and your variable might represent something else. So, what do they represent? Do you have any constants that are inside of this? Are there any constant values? Uh, Labeling your diagram might help you to put things together. Thinking about relationships between your variables, thinking about any important geometrical formulas that might come up. These are all things that we'll want to do when we create these functions. So let's take a look at our first example, which is this. We have the graph y equals 1 over x, and we're taking any point on that graph. So P represents any point that happens to be on the graph of that function. And f of x, the function that we're going to create, is going to measure the distance from P to the origin. So first thing that I'm going to do before I do anything else, I'm going to just quickly do a little sketch. This is not a well-labeled graph of 1 over x by any means. I just want to get an idea of visually what's going on. We should know that our reciprocal function 1 over x looks a little something like this. It's got vertical asymptotes and horizontal asymptotes, x equals 0 and y equals 0. I'm not plotting them. Like I said, this is not intended to be a well-labeled graph. This is just a little diagram for myself. So this, what I've drawn, this is y equals 1 over x. And P is going to be any point that happens to be on the curve. So that might be my point P. And what I'm going to measure for f of x is the distance from that point to the origin. So the overall thing is that f of x, my function, needs to be the distance from the origin, 0, 0, to my point P, which is any point xy that happens to be on our curve. So I know that for f of x, the distance formula is going to play a role in this. The other part is that x and y are not any two numbers that I feel like choosing. Here, x and y are related to each other. That if we're thinking about relationships between the first coordinate and the second coordinate, since it's a point on that curve of y equals 1 over x, then that means that whatever the x value is, the y value needs to be 1 over that x value. So instead of really saying that it's the distance from 0, 0 to x and y, you could say it's the distance from 0, 0 to x and 1 over x. This is how we'll get it from some expression that involves both x's and y's into something that's now just a function of x, something where we will only have x's in our expression. Okay, so now I guess the next part is let's actually do that. We said that we would have f of x being the distance from the point 0, 0 to the point x comma 1 over x. And we know the distance formula is found by taking square root of the x coordinates minus each other and squared, plus the y coordinates minus each other and squared, which, if we wanted to simplify that, there we go. And if I wanted to just make it look a little bit nicer, I could rewrite that x squared as being x to the 4 over x squared, so that I would have root of x to the 4 plus 1 over x squared, which would be, of course, root of x to the 4 plus 1 over root of x squared, which is something I could do if I felt like it. I don't really think you need to. This actually leads to a place where you need to be a little bit careful, because if you did decide to do this, you would have to be careful that when you say a square root of x squared, that you would write it as absolute value of x. And that's because no matter what value of x that you have, x squared is going to be positive, and so the square root of it is going to be positive. So in a sense, actually, you might actually be better off skipping that simplification and just leaving it in that first approach that I had of just leaving it as square root of x squared plus 1 over x squared. And that way you're not likely to make that simplification mistake. So there we go. This is something that I could say is my function f of x. And it definitely is a function for x, a function of x rather, because if you pick any x value you'd like, the y value you get, there will only be one y value corresponding to that x value. All right, let's do another one. Here we've got a semicircle of radius 3 with a center 0, 0, and it's above the x-axis. So I'm just going to do a little bit of drawing here for a second. If we were thinking about a circle with radius 3 centered at the origin, then you would know what the equation of that should be. That should be x squared plus y squared is equal to 3 squared, or 9. That would be a circle centered at the origin with radius of 3. But this is a semicircle. It's only the top half, the part that's above the x-axis. And so it's this part of the circle where the y values are only positive that we're interested in. And so actually I can get that by taking my equation for a circle and rewriting it. If I were to write it in terms of y, you'll notice that there would be two parts. There would be plus or minus the root of 9 minus x squared. The positive root, that would be the part that's above the x-axis, and the negative root, those would be the negative values for y, that would be the part that's below the x-axis. So if we wanted to think about what is the equation that we're talking about here for our semicircle would have the equation y equals positive root of 9 minus x squared. That would be the equation of a semicircle centered at the origin, radius of 3, and above the x-axis. All right, so that's our first part. The second part is that we're going to take any point on that semicircle. So I'm just going to draw my semicircle back in. There we go. That's my semicircle, and it's got the equation y equals root of 9 minus x squared. The next part that we're told is that we're taking our point in quadrant 1. So that means that the x and the y that we're thinking of here are positive values. That's something that wasn't the case in the previous question. That was why I said there was that issue of the absolute value that we would need to worry about, because x could potentially have been a negative number. Here we've decided that the point that we're talking about must be in quadrant 1, so that's my point xy. So since we're in quadrant 1, I'll make a little note to myself that x and y are both greater than 0. All right. So now the next part is that we're going to take our point that we have and use it to generate a rectangle. So what we're going to do here, it says, consider the rectangle with the corners at xy. Then there's negative xy. That would be the mirror image reflected across the y-axis. The point x0, that's the point right down on the x-axis, directly below our point P, and also negative x0, that's our point on the x-axis, directly below negative xy. So we've got these 4 points, and we're going to say that we are going to construct a rectangle with those 4 points. So the question is, what is the area of this rectangle? So the first thing that I'll note here to myself is that for a rectangle, we know that the area is length times width. And 2 things to think about here. Number 1, whatever the y value is, that's the measurement of how far above the x-axis we are. So the y value, you could think of that as the width of our rectangle. And x units across, that's how far you are away from the center to the outside. So the total length should be x units plus x more units, or in other words, that the length of our rectangle is 2x. So we've got a few things to fit together here, and I'm going to just summarize what we have on the next page. We know, number 1, that area is supposed to be length times width. And the length, we said, was 2x, and the width was y. That was the beginning of things. Length and width multiplied together gives me the area of a rectangle, and that there are y units in the vertical direction and 2x units in the horizontal direction. The other part, of course, is since we're creating area as a function of x, we need to make sure that what we have is strictly in terms of x. And here I've got x's and y's together. This is where I remind myself on the side that since x and y are coordinates of a point on the semicircle, I know that the y value is related to the x value by that equation. Y should be equal to 9 minus x squared square rooted. So that means that the area for my rectangle should be 2x times, instead of y, should be root of 9 minus x squared. There we go. And if we're thinking about this function, you might notice that this is a function where there's some restrictions on what values we can have for x. That was actually true for the previous function as well. The previous function would be, of course, undefined if x was 0, and that made sense because in the previous function, the x-coordinate was a coordinate on the point of the graph 1 over x. And x can't be 0 on that graph, so not a surprise there that f of x would have been undefined for x being 0. As a similar sort of thing here, we said that for this, x and y were our coordinates in the quadrant 1 for that one point that we had picked. And so the one thing that we know for this is that there's a restriction then, since you're on that semicircle, x could not be any larger than 3. If x were any larger than 3, you would no longer be on that semicircle because the semicircle only has a radius of 3. And that's one thing that you can notice here with our function a of x, that if you were to use a value of x larger than 3, that what would be inside the square root would be a negative, which would mean that you would no longer have something that's a real number. And we'd also said that x was inside of quadrant 1, which meant that x had to be positive. If x was not in quadrant 1, then you would have a negative value for x. If you were imagining x to be somewhere in quadrant 2, you would have a negative value, and that would mean that according to your formula for the area, you would get a negative value for your area, which of course also doesn't make sense. So for this, if I were to say my domain would be for this function all the values from 0 to 3. Now, I'm not including the 0 and I'm not including the 3. And it's for good reason. The reason being is that if we're thinking about picking a point in quadrant 1, remember that to be in quadrant 1 is to be in the interior of this quadrant. Being on the y-axis, you're not actually in quadrant 1. That's the borderline between quadrant 1 and quadrant 2. And being on the x-axis, you're also not in quadrant 1. That's the borderline between quadrant 1 and quadrant 4. So if you pick a point in quadrant 1, you can be as close as, but not at, the y-axis, and you can get as close to, but not at, the x-axis. So all of the x values that we would have would be somewhere between 0 and 3, not including the 0, not including the 3. The other reason why you wouldn't include 0 and 3 would be for the obvious. If you chose the x value of 0, then that means you don't really have a rectangle, you just have a vertical line. And if you chose an x value of 3, again, you don't really have a rectangle anymore, you only have a horizontal line. And neither of those have any area. So for this function, I would say that my domain would be the interval from 0 to 3. All right, one last little one to look at here. We've got a unit circle, and I've already given the equation of the unit circle, so I'm just going to sketch this really quickly. So we have a little unit circle, and P is a point on the circle in the first quadrant. So again, since this point is in the first quadrant, that means that x must be positive and that y must be positive as well. So there's our point xy that I'm picking. That's my point P. And it says, let Q be the point negative x, negative y. That would be in quadrant 3 then. Negative x coordinate, negative y coordinate. That would be my point Q. And then R, x comma negative y. Positive x value, negative y value. That puts me down here in quadrant 4. Couple of things just to notice about P, Q, and R. You can, of course, connect the dots to make yourself a nice little triangle. So that's what I'll do here. And the last part, the thing that I want you to notice about this triangle is that it is a right triangle, that it's a nice 90-degree angle that's going on there. And the reason I know that is because if you're thinking about points P and R, they have the same x-coordinate, so they're on the same vertical line. And R and Q, they have the same y-coordinate, so they're on the same horizontal line. So you've got a little horizontal line segment, you've got a vertical line segment, and those, of course, meet at a nice 90-degree angle. And so the last part about this is g of x is going to be the area of this triangle. And so here we'll need to flash back and remind ourselves that for the area of a triangle, it should be half of the base times the height. That's our formula for area of a triangle. So if we're thinking about this triangle, the base is the distance from Q to R. And from the distance from Q to R, kind of similar to the previous one, it's x units from the center to R, it's x units from the center to Q. so the base is 2x units. And similarly, for the height, from the center to P, it's y units. From the center to R, it's y units. So for the height, it's 2y. So that means that g of x should be half times 2x times 2y. Okay, so let's continue this on the next slide. I'm just going to simplify what we have here. Half times 2x times 2y, the half and one of the 2's cancel, leaving me with 2xy. And same thing that I said before, that since this is supposed to be a function of x, then I should only have, as far as variables go, x. This is where I'll need to remind myself that if we're thinking about being on a unit circle, then x and y are related by that equation. X squared plus y squared equal to 1. That means that y squared is equal to 1 minus x squared, or that y would be equal to plus or minus the square root of 1 minus x squared. Now, as far as the plus or minus goes, same thing as before. For the circle, the positive root would be the top part of the circle, and the negative root would be the bottom part of the circle. Since we're thinking about our point P being in the top part of the circle, being in quadrant 1, we're thinking of y being a positive value, in other words. That means we need to think about taking the positive root. So when I go back and think about this, I actually will take y being the positive root of square root of 1 minus x squared. And that's because we said that P, our point xy, was in quadrant 1. And if you're in quadrant 1, then that means the y value must be positive. So that's why we're not taking the negative square root of 1 minus x squared. Okay, so now we're pretty much ready to go. We can say, well, I'll replace the y with root of 1 minus x squared. And now we have a function of x that will give me the area of that triangle. So pick any x that you'd like in quadrant 1 that's on that unit circle, and you will be able to find from that the area of the triangle described by that point. Same thing that I would say, of course, as I did with the last one. If I were thinking about a domain for this, the domain would be the values between 0 and 1. Again, not including the 0, not including the 1. Since we're taking a point in quadrant 1, we know that the x values have to be somewhere between 0 and 1. If we took an x value of 0, then we wouldn't really get much of a triangle. We would just get a little vertical line, and that does not have an area. Same thing with if we took x as a value of 1, then that would mean we'd be having a horizontal line, really, rather than a triangle. Again, no area there. So if we want to come up with something that's in quadrant 1, x needs to be between 0 and 1. And if that's the case, then you'll get the other 2 points, and their area of the triangle that you generate from that would be given by that equation. G of x is 2x times root of 1 minus x squared.